Hi, my name is Alisa, and today our group will be presenting on graphene biosensor. First, let me go on to get to know graphene. Graphene is a single layer of graphite, which is produced by the process of exfoliation. Graphene is transparent, thin, flexible, have two-dimensional structure, and have a sheet-like appearance. Graphene is a strong material compared to steel and can replace silicon. Graphene also have a very good electrical conduction. So, here we will have a look at the graphite to graphene structure. Here shown that graphite is going through a process called exfoliation to produce a graphene-like structure. Next, we are going through the principle of graphene biosensor. Here we have 4 principles of graphene biosensor. First one is electron transfer materials. Second one is impedance materials. Next is field effect transistor, which is called FETs, and photon-phonon transfer. For the field effect transistor, we have 2 types of field effect transistor, which is FET-based biosensor backgate, and another one is liquid gate. For the photon-phonon transfer, we have 2 types. First one is graphene ECL enhancement, and the second one is for the quenching. For the first one, electron transfer materials, it is high surface area that expose all of carbon atoms to the target biomolecules, increase the sensitivity of the biosensor. Next is graphene can be exploited as an electron transfer material. After that, graphene can be used as an electric transfer medium in a sensor. Also, graphene able to act as an electron transport material by physical binding to the biomolecule and shifting electron through the bonding interaction. The second principle is impedance materials. The graphene is used to functionalize the electrode surface within a biosensor. Second one is graphene delocalize the pi network to form pi-to-pi stacking interaction, which can anchor the other pi conjugate molecules into the electrode. This modify the surface of graphene in biosensor without disturbing the desirable electrical conductivity properties. Next is higher surface area of graphene provide many anchoring or binding sites for both target molecules and fabricated metal nanoparticles. The third principle is field effect transistor, FETs. This graphene is used as a suspended FET in FET biosensor to produce an enhancement in the sensitivity. This principle is divided into 2. The first one is FET-based biosensor backgate. The change in a threshold source drain voltage causes the conductivity of graphene to change, allowing for a higher sensitivity to be recorded. And the second one is liquid gate. The graphene is very susceptible to a change in a surrounding liquid environment, whether it be by ion density or surface charge, which produce a higher detection sensitivity compared to the other non-graphene liquid gate in FET biosensor. Okay, the fourth principle is photon or phonon transfer. The mechanism that determines photon and phonon transfer through graphene is electrochemiluminescence, which is called as ECL. The first one is graphene ECL enhancement. Graphene's efficient electrical properties promote efficient electron transfer, which induce a greater concentration of intermediate species to higher electronic state per unit time. This increases the sensitivity of the sensor. Next one is graphene ECL quenching. Graphene quench the ECL mechanism due to resonance energy transfer. In the incorporation of graphene into the sensor increases the ECL intensity.
My name is Arif. I'll be explaining about the mechanism of graphene as biosensor. Now, graphene preparation is previously done via mechanical exfoliation, which is the repeated action of peeling of highly oriented pyrolytic graphite. But this method is also known as scotch tape method. Now, however, this method is not really suitable for large-scale production of graphite needed in different areas. But there are newly developed methods for such occasion or such use. This include chemical nanotubes (CNT), vapor deposition of metals, and arc discharge and reduction of graphene oxide into graphene. Alright, I'll be talking about first chemical vapor deposition, which is a simple, scalable, cost-efficient method to prepare single and few layers of graphene on various substrates. This opens a new route of a large area production of high-quality graphene film for practical application. Now, in general, CDV or chemical vapor deposition involves the deposition of fluids or gas and liquid sprays at high temperature to form either thin films on substrates or powders through filters. Now there are many forms of CDV such as hot wire CDV, thermal CDV, plasma enhanced CDV, radio frequency CDV, and ultrasonic spray pyrolysis. CDV synthesis of graphene can be carried out by at ambient pressure or vacuum by systematically varying parameters such as gas composition and flow rate, temperature, and deposition time. The carbon precursor in CDV is methane. Now, by using diluted methane, single and few layers of graphene, less than 5 layers, were grown, while using concentrated methane result in multi-layer growth. Now, other carbon precursors that can be used in CVD, such as ethanol, isopropanol, ethylene, and acetylene, and also others. Next is the unzipping of carbon nanotubes or CNTs into monolayer graphene. Now, this method of unzipping single-wall carbon nanotubes to form monolayer graphene by harsh acids and the right thermodynamic conditions. Graphene nanotubes or GNRs, a method to produce GNR is through controlled unzipping of CNTs using the AR plasma etching method. Arc discharge. Arc discharge is a versatile and low-cost method for producing various kinds of carbon nanomaterials. Compared to other methods, the graphene sheets synthesized by arc discharge have merits of good dispersibility in organic solvent, few defects, and high thermal stability. In the arc discharge techniques, graphite rods with purity of 99.99% are used as electrodes for high voltage arching. At extremely high voltage between the electrodes, they are separated by very small distance. Very high electric fields can be produced, leading to instantaneously sparks in like a welding process, if you will. Now, the forearc during the discharge process is the end product that contains the carbon nanostructures. To prepare pure few layer graphene, a direct current arc discharge of graphite evaporation was carried out in a water-cooled stainless steel chamber, now filled with different buffer gases after evacuating the chamber by a mechanical pump. When the arc discharge process ended, the generated soot was then collected under ambient condition. the soot deposited on the inner and top wall of the reaction chamber was only collected in order to exclude the relatively heavy products, which is amorphous carbon nanoparticles or multi-layered graphene sheets dropped to the bottom of the chamber during the arc discharge process. Now, different discharge atmospheres may induce different chemical bonds that can also cause the prepared graphene sheets to have different properties. Direct current hydrogen discharge evaporation of pure graphite electrodes in various gas mixtures can be used to mass produce high crystalline few layer graphene sheets. Okay, now the last point of mechanism is the reduction of graphene oxide into graphene. Now, graphene oxide, GO, was synthesized by the strong oxidation of flake graphite using exit via Hammers method or modified Hammers method. GO, an oxidized form of graphene, is decorated by hydroxyl and epoxy functional groups on the hexagonal network of carbon atom with carbonyl and carboxyl groups at the edges. Now, GO is highly hydrophilic and form stable aqueous colloids due to the large number of oxygen containing functional groups, as well as the repulsive electrostatic interactions at the edges of the pellets. It is reported that, or it is experimented that GO can be reduced via thermal, chemical, electrochemical, and also laser scraping methods. That's all for my part. I would like to give to my group members to continue for the next part. Thank you.